Hello and welcome to this webinar today. We want to introduce to you our new solver that is actually targeted to simplify thermal simulations for all thermal engineers and is specifically helpful for electronics cooling applications. And that's why we're going to have a dedicated webinar for this with the model that you can see here on the right side as kind of the main application area, an EV inverter model, but we will also dive a bit into the details of the method and give you a good overview how you can use it for your application. My name is Alexander Fischer. I'm product manager at SimScale, responsible for our electronics cooling offering, and that's why also this solver is very important for our roadmap and the solution that we are offering for these kinds of applications to you. Quick look at the agenda. So I want to give you a quick introduction to SimScale in general, and then show you how SimScale empowers engineers in general as well. And then make a deep dive into what's new about the conjugate heat transfer solver with the IBM extension. What's the benefits of this solver and why is it especially helpful for thermal simulations? And then we're going to have a quick look at a case study. So the inverter model that you've now already seen, I will show you on the live platform how you set up such a simulation, how you can do it yourself, how you post-process the results, and essentially teach you all about these kinds of simulations. After the live demo, we will have a quick Q&A. So I'm very happy to answer your questions. If you already have questions that arise during the presentation, please be so kind, directly post them so that we can later on answer them. Don't wait for the end. We can already coordinate them during the webinar and answer them at the end. Good. So a quick introduction to SimScale. The company was founded in 2012, so we're around for a bit more than 10 years, have offices in Munich and in the US. We have, meanwhile, I think a bit north of 130 employees across all time zones, essentially, as we are quite internationally enabled company. We have lots of users as we are all cloud-based a tool that is very accessible to everyone. Some of these users are paying customers, others are partners or academics, and also some community users that provide public content for others to learn and help and produce great content. As you can see, there's many projects, many simulation jobs that have been run on our system. SimScale was actually founded to empower engineers, so we want to make high fidelity simulation accessible to every engineer, and to do so, there are a few obstacles that need to be bypassed, and we're trying to do so by providing a all cloud solution. So it's a cloud native simulation platform that you can use in bigger organizations, but also in smaller sized companies. That addresses a couple of problems that were with traditional simulation tools. So I already mentioned it's cloud native, so essentially you don't need any remote desktop or anything. You can just type in simscale.com, log into your account, start simulating in a standard web browser. That's everything you need apart from an end device like a laptop and a stable internet connection. It's one platform that tries to cover a broad range of physics so that kind of all the engineers can work together on one product, but for many applications. So that's why you can see here that you can do flow analysis, thermal analysis, structural. We always also look for partners and implementations to expand this range of physics, specifically for electronics applications. Obviously, all of these areas are important and can be helpful to be used in your organization. We have a real-time collaboration and support, which we are also quite proud of, as when you're working on SimScale, you don't need to file any tickets if you're having problems, if you don't understand how you would go further, or you have questions about a simulation, you can directly reach out to us. I'll show you this during the live demo as well, but you can see on the right-hand side already that we have an interface where you can see if we share a project with other users, with maybe your teammates or our support team, that you can see when people work on your project, help you, or just view the project essentially. And by that, you can essentially, when you have a problem, you can reach out to us and we help you directly in this moment where you need the help. You can use SimScale on any scale, so there's practically no limits in regards to simulation size, number of parallel simulation, number of users. It's all enabled essentially by a very scalable cloud architecture. So whatever you want to do, you basically will not reach our limits. So we're really interested in the use cases that you have, and the more simulation can benefit your business, that better also for us. So that is really great and what we're looking for. And it's quite cost effective, so you can use simulation really economically viable, meaning that you can start already with a few users. You can do all of these parallel simulations, to reduce the time to market, reduce the design cycles, and benefit as best as you can from engineering simulation in your design process. For today, I want to show you this kind of inverter design. We will mostly focus on the method and why the Immersed Boundary Method is really helpful for running thermal simulations on SimScale. But in general, obviously, what you would be doing with these kinds of models is trying different designs, try different variations, for example, in this case, on the liquid cooling channel to get the best out of it. In this case, you can see that probably this is going to be a trade-off of a pressure drop that you have in the liquid cooling channel and the cooling efficiency that in this case would be mostly targeted at the MOSFETs that get hotter from the switching losses when driving the essentially electric motor. Great. So with that introduction, I want to give you some insights into the Immersed Boundary Method and what it actually means. You can see here already some images. Also, you can see the meshing approach that is taken on the right-hand side. It's important to note in the beginning already that this is not a completely new solver. It's an addition on the conjugate heat transfer offering that targets thermal simulations in general. So it's really an extension to this solver that just changes the way how the meshing is done and how we can treat original models. So as you can see, CAD as manufactured is written here, and it's a layer on top of the standard implementation. So nothing completely new, which means it also benefits from all the development validations, etc., that have been done on the body-fitted CHT simulations that we could do already in the past. So why even the Immersed Boundary Method? So first we need to look at the challenges that electronic thermal simulations face essentially. That is mostly centered around the CAD models that are required for these kinds of simulations. So CAD models are usually huge assemblies of many parts. As you can see, one example here on the right side, often these CAD models are assembled from different sources or different tools. So it might be that different teams have been working on such a model and it's then combined, but it can be also that many of the parts are actually bought from different suppliers, and the CAD models are then just downloaded from the supplier websites, come from different CAD tools, or might be provided in generic CAD formats like STEP or IGES. And then the quality of these CAD models often suffers from these different tools and different sources, and you can't really control that or change it in-house. So that's just a challenge that comes by nature with this in this field. Often the models are also very detailed, so topological and geometrical details, where geometrical details, for example, would be screw threads, cables, etc., while topological details would be, for example, logo imprints, as you can see again on the right-hand side, that are just face imprints that in a body-fitted kind of meshing would need to get resolved, as the mesher does not understand what's really important or not important for the objective that you're following with your simulation. So I already started mentioning the challenges for the engineer. So these details require a high resolution in meshing to be even resolved, but they also need an even higher resolution to get acceptable mesh quality. And the mesh quality is quite important for your simulation to converge and actually be stable and successful. So even though you're not interested potentially in the areas where these details sit, you still need to really resolve them for the whole system to be solved in a stable way. That's really a pain, right? And that means essentially that you can pick if you go very, very fine, spend a lot of time in meshing, or if you spend a lot of time in simplifying and cleaning up your CAD model, and that can be easily a longer time frame than the runtime of the simulation. It can be hours, can be also days. That's really, really painful time that gets lost in the design workflow. So in the end, it's always a trade-off. Where do you lose the time? But what is clear is you will lose time either in manual effort, or the simulation turnaround times will suffer from the high mesh resolution. And you could even face the problem that you have recurring issues with each design iteration, as again, you need to combine it with potentially parts from other suppliers, etc. So that really, really hurts, as what costs you so much time often are insignificant parts that are not important for the thermal behavior, but need to be considered. Otherwise, the whole system cannot solve well. And that is exactly the challenge where IBM comes into play. So it's just a great solution to exactly that problem, because Immersed Boundary is based on cartesian meshing. So instead of meshing something like here body fitted in detail, you can see here an LED luminaire, and you can see the spring on the right hand side that is used to plug this LED luminaire into the ceiling. You can see that now there's a lot of elements needed to resolve the spring, even though obviously it's not thermally significant. I can, in this case, just delete such a part. In other cases, I would need to delete it and then fix some gaps, other problems in the model, and that takes me a lot of time. On the contrary, if you do Cartesian meshing, we just now embed our CAD model into a Cartesian grid that still refines towards important parts and surfaces, but does not resolve exactly the geometrical shape of the parts, but rather kind of embeds them into this grid. So that allows us to implicitly defeature some of the little details, or simplify details into just coarser resolution, if you will. And topological details that I mentioned before, like logos, etc., they don't play any role at all, because they are just completely ignored by that meshing algorithm. So it's really helpful. Another benefit is for sure that as we have only Cartesian like hex cells, we have kind of a perfect mesh. Obviously, there is some transition between larger and smaller cells in the refinement regions, but we don't have really terrible skewed elements that screw up essentially our whole mesh, or you might know these type of elements if you have small gaps problems around these, etc. So that's great. And as the geometry is just embedded and not completely resolved, the interfaces between, for example, the solids and the fluid region, or solids and solids, they are rather treated now numerically on the solver level. So there it is taken care of that the heat transfer between parts, or the convective heat transfer from the solid parts to the fluid, is taken into account based on the resolution that was applied around these surfaces, and that this is correctly taken care of, instead of doing this by fully resolving the geometry in the mesh. Another advantage of the method is that you can use flow domains as part of the CAD, but you can also leave them out and just essentially cap internal flow regions with cap surfaces, or you can put a simple primitive box around your model if you have an external flow problem and run with it. So you don't need to do any Boolean CAD operations, and you don't require the quality in the CAD that it needs to do these kinds of operations. So it's really great because the computing resources that you will put into this, so the runtime and the instance cores that will do the numerical treatment or the computation for you, they are really targeted at what is physically relevant instead of actually focusing on what's geometrically challenging. And that's what you want to do. Great. So I mentioned already now what the IBM method does. We will take a quick look at what benefits it provides for your simulation. So how do does this solution affect what you're doing later on? Let's take a look now at a chart that shows us, for example, an important result like temperature, like the max temperature of our chip for the inverter use case. And we have here on the x-axis the resolution from coarse to fine. So that corresponds to mesh size or computational costs. We will look at the body-fitted approach and the simplified approach, the body-fitted approach and the immersed boundary approach. And we will look at an original model without any CAD simplification and cleanup. And we will look at a model where we did all of these steps to get it down to also make it really usable in a body-fitted scheme. So at first, oftentimes we will have the problem that the original model cannot be even used with a body-fitted scheme. There will be overlaps, there will be quality problems. So I can either not even mesh it or run the simulation with a decent mesh quality, or if I can, it will be a really huge mesh size. So in many cases, it's not even an option to use this directly, but rather simplify it first to get a body-fitted simulation. When we do this, we will still require significant mesh resolution to even run the simulation, but then we can increase the mesh fineness to get closer to the exact solution that is here mentioned as a reference solution that you might get from a mesh convergence study or from physical experiment. And the higher kind of our mesh fineness is, the better our solution will get. Now we want to take a look why the immersed boundary method now really helps us do simulations more early and spend less computing resources on already getting valuable results. So first, I will bring in the simplified model with the immersed boundary method, where you can see that essentially it behaves very similar to the body-fitted approach. But what we can now do is we can we can already run simulation on much coarser levels, and we can get better results for very coarse simulations because we can target the mesh resolution at the areas where it matters most, instead of filling essentially or adding elements where geometrical details require to do so. So that's already a benefit, but it's still the simplified model. So we don't really want to work with the simplified model. And that now shows up when I bring in the original model, because here a huge benefit of the method lies, because both the original and simplified model will behave nearly the same, as the implicit defeaturing and simplification will lead to the original model then in the simulation context looking almost the same as the simplified model. So we can save essentially all of the time of simplifying the model and get a very similar solution. Additionally, it's quite helpful that even though obviously for very coarse resolutions, we will not reach the same accuracy as for fine simulations, also for the IBM method, in the end, for very accurate or kind of very high resolution meshes, all of these simulations will lead to very similar or the same results. But we can already now use an area where we have decent results very early, for example, in the design process, and iterate earlier and save all of the time of simplifying the model by running IBM simulations on the original model. And that's the whole trick, or that's really the benefit that you get from using IBM on original CAD models instead of spending all of the time to simplify and clean up your CAD. Great. So we look now at the model that we will take a look on the platform. This is an inverter model, 6 phases, 12 MOSFETs that are required for the switching frequency, and all of the parameters are given here. We want to take a look at the liquid cooling channel and how effectively it can cool down the MOSFETs. And you can see here on the right-hand side that we pick essentially the MOSFET that has the highest temperature in our setup, and we will compare it for the different simulations that we've just theoretically discussed in the chart on the last slide. So we'll be looking at the max temperature. Obviously, we could also look at other results. Very important is the pressure drop of the liquid cooling channel, of course. Great. So let's take a look at this table. I want to go through it step by step so that it's not too overwhelming. You can see here again simulations based on the different method and model. You see the finesses that were used in the user interface. We will visit this in a moment when we go to the live demo. You see the mesh sizes that differ a lot and the resulting computational core hours. And you see the temperature in degrees Celsius, the temperature rise above the liquid cooling temperature, and you see the difference of the solution compared to now a base solution. And here I picked the finest solution on the original model with the body fitted approach. So here I really went through the pain meshing this in very detail up to a 34 million mesh to run the simulation on this original model. For other models, it might not even be possible, but for sure you will require a lot of computational effort to do so. So, as I mentioned, for both models that we run body fitted, the original and the simplified, we get with the default meshing really high mesh counts, 34 million and 19 million. So we also require quite some computing core hours. Core hours just means essentially if I'm running 365 core hours on 100 cores, such a simulation would take me 3.6 hours. We can now do manual effort to get this mesh size down and even run simulations by doing some manual mesh refinements, coarsening, where we know it's physically irrelevant, but obviously we need to pay for that with manual effort and time, and it requires some expertise, but we can get the mesh down to a certain level. The great thing is that for IBM, we don't even need to do this, right? Because for IBM, I can run different finesses and start with a mesh that is as coarse as, in this case, 170,000 cells, but I can go really step by step to a finer level, reaching the area and then also reaching the accuracy that I would have with a body fitted mesh approach. That might not be the case if, for example, boundary layers are very important. So if I'm really interested in a result that is, I don't know, 3% off for the flow pattern quantitative values, but for the thermal behaviors or the temperature values, usually that is not required, and it get quite some decent results with the simplified IBM method. And additionally, we implemented a way how you can run such fineness studies automatically. So as a parametric convergence study that helps you judge the quality of your results, as you can kind of go very, very coarse, right? So numerically, then your results still are very sensible, but it might be off to a larger extent that you would expect it or you would need it to make good decisions with your model. Great, so much in regards to the theory. Now I'll just close the presentation, and as you can see, I'm here in my web browser, so I will just switch to another tab, and we can take a look now at the SimScale user interface. So I opened up now this project of the inverter. You see here on the left-hand side our geometry and simulations navigation panel. You see now immediately a result of our inverter case, the temperature in this case here on the capacitors. I can turn this around and we can take a look at the MOSFETs as well. And you can see that on top we have here a few options for you that are maybe a bit untypical for simulation environments. So I can share my project. For example, if I want to provide results to a colleague of mine, give him, for example, edit permissions or view permissions, or I can share my project with support. That makes sense essentially if I have a question or if I have a challenge that I want to get input from the SimScale support team. In such a case, it always makes sense to share your project, and then you can directly reach out here on the right-hand side and talk to my colleagues in the support team. So you see here Ali, Johannes, and Khan. So these are real people that sit next to me in the office. And get essentially input on your simulation at any point in time. Great. So what we want to do next, we already now took a quick look at a result view. We want to go now step by step through the setup of such an IBM simulation. So I'll go back here to the geometry section. I can open up here the geometry model. So this is now the respective view. You can hide a few parts to look into the insides. We have here the MOSFETs of the model. We have here the capacitors. So this is the simplified version. I also brought in obviously the original model. You will see that we will have a lot more details now in this case that have been removed for the other models. So the MOSFETs were essentially just boxes. Here we have all of the little details that were in the original version of this EV inverter. Great. So if you want to now run such a simulation, you can see that I did the study in this project beforehand. So I ran all of these different versions. We would just now set up a new simulation, and you can see here that I can now select between conjugate heat transfer, which is the body-fitted conjugate heat transfer module, and you can choose conjugate heat transfer IBM. That's now, you see the little Cartesian mesh that indicates here that this is a different method, but still the same physics. So we are solving convection, conduction, radiation in both of the tools. It's just this additional layer of treating the geometry and meshing differently. Good. Then the setup works very similar or essentially the same as also for the body-fitted approach. So you don't need to learn anything new here. All of these solvers work very similar in SimScale. So we just add our materials, like we could add water glycol, assign it to the flow region, save it, and do the same for the boundary conditions and the power sources. So for example, for the MOSFETs, we would add absolute power sources, select these parts, and define 50 watt for the power dissipation. How this looks once you're done, I obviously in this case already did. So let's look into this setup. You can see here now I set up all of the fluids, all of the solid parts, aluminum, copper coins on the PCB, the MOSFETs, the velocity inlet here, where the cooling comes in with the setup temperature and flow rate, and the pressure outlet on the other side. And then I added as advanced concepts the MOSFETs as a power source and the capacitors also as a smaller power source at the bottom of the board. So that's kind of the completed setup. If you want to run such a simulation now in SimScale, you can just use essentially our default meshing. So if I click here, reset, you can see that I can use here, for example, level 5 meshing. That's our standard mesh sizing and run it. Or I can use a parametric study. That means I can define now different fineness grades for the meshing. So from 0 to 10. Now it will run 5 different simulations and give me the decisive results, like the critical temperature on the MOSFET. So define it here. Please give me the temperature on the surface of this MOSFET for all of these simulations. As you can see here we have the results of the study. I'll quickly show you how that works. So I would click run experiment. I would call it mesh study, and then start the simulation. And next, you will see that we get a new simulation run that exists of multiple different mesh sizes that get all started in parallel and executed in parallel as well. Okay, yeah, here it comes up. So I can follow each of these runs separately. It will tell me essentially for how long this runs, how many core hours I'm consuming. And once it's done, I can access all of these runs separately, one after the other again. And click into solution fields, look at, for example, temperature plots over the runtime, or as I did before, open up again the solution fields and then do some deep dives on what's mostly interesting. How does the flow pattern look? Do I maybe have also prepared this prior? Do I have maybe recirculation zones in my simulation results? Can I improve the liquid flow channel in these regions, etc. What I didn't tell you yet is that you can obviously also access other projects like public projects or our forum. So I would essentially just incentivize you that you go in here and create your own account, give it a shot, try your own application, and then you can check essentially all of the different resources to learn and also understand how to do simulations on your own. So we load the results here again. You can see on the left-hand side the filter pipeline that we have. You can go through here, show different result fields, use cut plots to display, for example, flow patterns, etc. I'll wait for this to be fully loaded, and then I'll show you quickly what you can do here. So if I enable, for example, this cutting plane, it will show us the velocity magnitude inside of the liquid cooling channel. And we can also display here, for example, little arrows that show us how the flow goes through this. Do we have recirculation zones that would be very problematic in regards to cooling this efficiently? So all of these things you can do. You can also do different cut plots to look at the mesh details, understand if you want to potentially add mesh refinements somewhere, or if the default meshing that you set is absolutely good enough in your case. So if I clip the model here, we'll get a detailed look on the inside of this model and do the post-processing as if we would have done if we would have used a body fitted approach. Great. So that's what I wanted to show you on the platform. I'll quickly jump back to the presentation and give you a quick summary of what we've seen. So you learned how to run a simulation on SimScale, in this case, using the Immersed Boundary Method. You also learned that this doesn't differ from other application or other simulation types on SimScale. It's just the method that is different, but that should enable you to run simulations much earlier and simpler. And we want you to really take this, the chance of having simulation accessible and easily usable, and make your application the next application on SimScale. And we would really ask you to get in touch and talk to us, get us involved, and then we want to see how your simulation turns out and which great design improvements you can base on these simulations. Great. So I already thank you for listening in, and now I will switch on my camera and I will skim through your questions first, and then we'll answer a few of them. So great. I'll quickly check. A few are already in. I would ask you if you have additional ones, please still fill them in. I will take a few seconds ahead of any question to try to still answer those. And I will directly start with the first one, that is, how can I get access? So that's a pretty simple one. It's really just a module that we put on top of our current conjugate heat transfer offering. So You can run simulations with the IBM method, as you can do with our conjugate heat transfer solver. So there's a kind of a range of simulations that you can do within our community plan. And if you decide essentially to run SimScale commercially, you can buy a certain package and run then simulations, but there is no special IBM plan or anything like that. So it's available every time when you acquire SimScale or if you use it publicly. Then there's a question about when I would recommend using IBM and CHT or vice versa. So it basically comes down to the objective. I mentioned during the presentation that you wanna use IBM mostly if it's about thermal simulations, because in that case you usually don't go down to the last little detail of the flow field. In such scenarios, I would rather recommend probably using a body-fitted mesh approach, because in that case you would extract once your flow region and then you would iterate on this flow region. So you would not bring in all of these different parts, all of the geometrical details, the logos, the imprints, the screw threads. So you would rather operate on one part only, and then it probably makes sense to run on a CHT. There's nothing bad about a body-fitted approach anyways. It's just a great tool to run accurate simulations. It's rather that often you're just not capable of doing this because of the complexity of the CAD. So in many situations, when that's the case, then you would opt for an IBM method, and you could run it essentially just because it saves you the time of simplifying and cleaning up the model, or you could start running simulations in scenarios and circumstances where you would not have been capable in the past to run simulations at all. Great, then let me check again. We have one question is dedicated to the feature set. If there's a difference between the solvers, there's essentially no difference. So we spend a lot of time now after the beta phase for this solver to add new functionality and get them essentially on an identical level. There might be one or two features that we are working on right now, but essentially you probably won't find these. So it's basically the same feature set. There is also one question about what geometry input is required. That's an interesting one, because essentially it doesn't differ from what's in general required as a geometry input for SimScale simulations. So we support essentially kind of all standard CAD tool and CAD formats. You can bring in your assemblies from different tools, SolidWorks, Onshape, Inventor, etc. You can also bring in IGES or step files, so generic formats. But what is probably interesting now in regards to Immersed Boundary is that as we don't really mesh the model in a body-fitted way, the quality requirements regarding these bodies is really much lower. So it's also possible to run IBM simulations on faceted or mixed parametric and faceted models. So if you have a model that is based on some kind of facetation / tessellation, like a gyroid or additive manufacturing based type of model, then you can also use these and run them with Immersed Boundary, as again, simply then the faceted representation of this geometry gets immersed into the Cartesian grid, and you can run a simulation as if it would have been created in a parametric CAD environment. So that is quite powerful. In general, no difference to other simulations, but the scope is even a bit broader or a bit wider. Good, and then I have a last question that I want to address, that is running geometric studies. Would this work reliably, specifically now with IBM? Yeah, it works reliably. So how you would do geometric studies in SimScale in general would be that you just bring in your new CAD design or your CAD variant, and then you would just copy your simulation of the last design, update the geometry, and what we do then is that we show you a report that gives you an indication of how many of the settings that you set up are mapped. Usually this should be all, right? So probably you're just changing some parameters like the flow channel thickness, or for heatsink applications, maybe the thickness or the length of the cooling fins. Then it will map everything, and you will see essentially that everything has been updated. If you make some bigger changes, you might bring in a part from a completely different source, like a parametric heatsink replaced by a gyroid heatsink that was created in a different tool, exported as STL geometry. Then the mapping, of course, for this part cannot work. There's no connection in the CAD files that we could detect, but then we report to you all of the settings that need to be updated so that you can just start the simulation run again. So here it's quite helpful. It's also helpful that you can run the simulations without bringing in the flow region up front, because the flow region usually is just the negative of the solid part. So you're kind of doubling the complexity of the model, that all of that needs to be updated and mapped. So you can also here just use the primitive setup, or by putting bounding caps on the internal flow channel, and then bring in your new CAD design, to kind of put it into the box again and run the next simulation. Great. So I don't see any new questions coming in. I would ask you, if you have new questions or additional questions that come up after the webinar, please reach out to us. You can see it on the slides that I've shown you. We will upload the webinar for on-demand usage. You can just reach out to me directly via my email address, or even much simpler, create an account and start communicating or discussing with our engineers on the platform, and directly reach out to us via the chat functionality. Thanks for your attention again, and have a great day.